Okay, so if we did electric fields yesterday, we're on to magnetic fields and still working through particles and waves. Okay, now electric fields are quite straightforward because we worked out that electric fields gave us electric field lines and the particles would always accelerate in a direction that was parallel to electric field lines. If it was a negatively charged particle, it might go in the opposite direction to the arrows on the field line, but it would be traveling in a direction parallel to the field line. So this is not quite so simple. So same direction, just discussed that could be opposite or should probably be parallel to the electric field lines. In a magnetic field, the particles accelerate in a direction which is 90 degrees to the field lines, and it's also 90 degrees to their own velocity. So that makes things a little bit more complicated. Okay, so at the heart of all this is this 90-degree thing. So here, using the magic of my three-dimensional art, I present you with three orthogonal axes. Now, orthogonal is the word they should teach you in maths for things that are at 90 degrees to each other. So, you know, the idea here being that that is actually on the page that way. This is coming out of the page towards us, and that is at 90 degrees on the page. So I've got, maybe if I just abandon my diagram for a second and say, okay, there's two that are at 90 degrees. And then the next one is coming at you, so it's coming out of the page and like that. And I now have three orthogonal axes. And that's at the heart of all geometry as organized by René Descartes, Cartesian geometry. So, Cartesian coordinates. So there we go. Now, I need to then say I'm going to do this for force, magnetic field, and electric current. And the trick for this is to say, okay, there's my orthogonal axis. I'm going to use my magic fingers. And using the power of deep art, I have the fingers. And so the fingers here are like that. And you've got to be really careful to keep these at 90 degrees. Don't start going like, keep your fingers at 90 degrees like that, and keep your thumb vertical and keep it like kind of honest. So here's mine. Here's the notes for that then. The thumb is for the thrust, which is also the force on the particle. So this is the force on the particle, and it is first finger field. Remember, that is magnetic field because the whole topic is magnetic. And the second finger is the current, which is actually the particle velocity vector. I've written current because I was taught this in terms of electricity, about wires jumping around and how motors work, which is kind of, it's all the same rules. So this is the particle velocity, the current. I'm imagining my flow of particles as a flow of current, and I'm using my left hand for positive particles, and I'm using my right hand for negative particles. Cool. Let's move on. Okay, next step, arrow notation. Now, on diagrams, we have this weird arrow notation because we're going to try and do 3D on 2D. So we say, as if it's an arrow, if you were looking at the back of an arrow, so say you had an arrow that was going down into the page, you would see the cross of the feathers or the flights on the back of a dart or something like that. So you'd see the cross, so that means field going into the page. And if the arrow is coming out of the page at you, you might say, hold on a second, would I see the feathers as well? Maybe. But imagine you're just seeing the point on the very front of the, you're just seeing this point on the very front of the dart. So maybe better to think of it as a kind of, as a dart and say, you've got the flights on the back and then you've got the really pointy end bit. Okay, into the page, coming out of the page at you. Okay then, so let's have a go. So, now, I've got a diagram here. Here's my magnetic field lines going from north to south. I've drawn them in the poles of my magnet to show you. And I've got a particle, and the current of my particle, so let's just imagine I've got electrons. So I've got electrons. Now, electrons are negatively charged. So that means I use my right hand. This one. And I have to now sort it out and say, okay, first finger field. First finger, my magnetic field is going that way. Second finger is current, which is the flow of the particle. So my electron is going down into the page. So now I'm like that. And now my thumb is pointing up the way. So I know that the force on this particle would be that way if this particle is an electron. Okay, let me go through that again. Negatively charged, right hand. The current is second finger current, and that is the way the particle is moving. So it's going down into the page because of the arrow notation. And I need to rotate I can't mess with my fingers stay in the 90-degree pattern. I have to rotate my hand until the field, first finger goes with the field, the second finger goes with the current, and my thumb gives me the force or the thrust, thumb for thrust. Okay, that's that one done. Now, what are the weird anomalies in this? Well, the anomalies in this are, if you have a particle that is traveling along a field line, it won't experience a force. So, two things. Okay, if a particle is moving in a parallel direction to the field lines, no force. If the charged particle is not moving at all, it's just stationary in the field, in the magnetic field, a charged particle will not experience a force unless it is moving in that field. And it cannot be moving, it will also not experience a force if it's parallel to that. So you could get caught out if you don't know those two key facts. Okay, and so zero velocity and then parallel to the field lines. What does that look like? I think I've got a diagram of that. Parallel to the field lines is basically going this way. So here's the north to south field lines. Remember, this could be vertical, it could be orientated in any direction. And so the velocity, I would think of it as going along a field line, but in reality it's any path that's parallel to a field line. That's the math symbol for parallel, we know that. Math symbol for perpendicular? You must know that. What do they teach you in maths? So, no force experienced. This electron will not experience a force. Okay, what's left? Curved paths. Well, magnetic fields do give our particles curved paths. And that's the whole point of what we're going to go on to use them for. So when we go into particle colliders, we need to have our particles whizzing around in curved paths, and the magnetic fields do that. So let's talk through how that works. Imagine I've got an electron going straight into this region of magnetic field, and the magnetic field is going north to south. So remember, magnetic field lines always go north to south. It should have arrows. So it's an electron, so I need to use my right hand. Negative charge, right hand. Okay, I'm wondering, some of you need to write positive on this hand and negative on that hand. Anyway, so I might think, okay, first finger field, second finger current. That's a bit awkward because basically, if that's the field and the electron's going that way, it's going to be pushed vertically upwards out of the page. So this electron would actually follow some sort of path where it's going to go in and then be, as it travels through the field, be curved, and then at that point then carry on in a straight line after that. So that's kind of weird and difficult to draw on this diagram. So how can we make it easier to draw? It'd be a lot easier if we reorganized this and looked at this from a different perspective. So let's look at it from a perspective where my magnetic field is now going down the way, down into the page. So you could say, hold on a second, have you just turned this diagram from being like that way and just brought it up to the vertical and said, okay, I've got my North Pole up here, I've got my South Pole under the table, and my magnetic field lines are going down, 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 perpendicular to the page, into the desk. So my magnetic field lines are going invisibly, well, they're all invisible anyway, down into the page, and here's a proton. Proton, positive charge, left hand. So keep your angles true. Motion of the particle is the current, so that's the second finger. The field is down into the page. First finger field, second finger current. In this region, now you don't have to actually draw these arrows, the back of the dart, as it were, all over this. You can just label one part of it and say the whole region is down into the page. So here's the thrust direction then, across this way. So my proton's going to, if it goes in a little bit, just a little bit, we know in that first little section, it's going to be experiencing a force. Let me just draw him in. Don't know why I've made him a masculine proton. You might not want to discuss his gender. So he's going to experience a force that way. So he's actually going to start curving round this way. And when he's gone a little bit that, because he's experiencing this force pushing, he's got a velocity in this direction, but he's experiencing a force pushing him that way. So the result of that, after a while, is he's going to change his direction. And when he's got to here, if you remember, he's now got a velocity this way. But to work out the force, I need to use his velocity for this finger, for the current. So if his velocity is now over here, now the force is no longer, the force that was, when his velocity was straight down the page, the force was over that way. Now his velocity starts to curve around a bit, his force is always at 90 degrees to his velocity. So his force vector starts to curve around a bit as well. So that was the initial force. I could have called that F1. This is F2 a little bit later. So now he's going to try and carry on going this way, but he's always going to be pushed a bit that way. So he's going to curve round. And depending on how fast the proton's going and how strong the field is, he'll follow a curved path through, because his next force vector would be, I can't draw it, I stupidly wrote F2 where I want to put that arrow in. So F3 would be the same size force as that, but I've just, honestly. And now, so if he was going, he's going to continue to curve. There's no reason why it's going to stop curving. It's going to continue to curve around. And if this was a really strong magnetic field and a really slow proton, it will continue to curve. And then when it gets out of the region here, okay, now at this point here, the force must have been at right angles all the way. Because, let me do it again, first finger field, second finger current, these two are always at right angles. So you can see my force vectors should have been always the same size, F4, F5, F6, there. And once it comes out of the field, it will continue in a straight line, assuming there's no other random fields to push around this proton. So that's my proton taking a curved path in a magnetic field. Now, if the magnetic field had been weaker, the proton might have taken a curved path that was only very slightly curved and then gone, so it might have had a much smaller deflection. And so there are a variety of options. It could have done that, or it could have just curved a bit more and then gone to. Notice that as soon as it comes out of the magnetic field region, it's going to straighten up. And I'm kind of running out of colours. Oh, I don't know if it's orange. So there were a lot of options for this, but you notice it was always going that way. It was always curving round. So there we are. So charged particles will travel. Now, if this proton had been an electron, then that diagram would really just be reflected in this axis, and it would all be over here. My curves would all be there. Oh, I'd have the similar curves, the options for different speeds and magnetic field combinations. Okay. What's the final point? The final point was, I thought I could maybe go 3D, and then I thought maybe I was a bit too confident. If my electron goes, this is an electron, so I'm going to use my right hand, and I'm going to attempt to go 3D, which is, if my electron goes in, at the point where it experiences this force, it's going to experience a force. Oh, negative charge, electron. I'm trying to draw a 3D, and my field is vertically down, and my current is that way. So my hands are like this. And so the force is going to be at right angles to its velocity this way. And have I got that right? Current, field, yeah. So that means it's going to then sort of curve round, and it could curve around that way until it comes out of the magnetic field, and then it will go straight. So not sure if attempting to be 3D was sensible, because all these green lines are actually on the same flat plane, as if you would put a sheet in between my two magnets. So they're all on the sort of flat surface. Anyway, so those are all my little force vectors that acted on the electron when it was in the magnetic field at little intervals that I decided to spot. And then when it leaves the magnetic field, it continues in a straight line. So that's good. Okay then. So, plan is, you go back through the magic finger routines by looking in the blue book at pages 105, 104, 5, 6, questions 19 to 23 during today's lesson, so we can discuss and get the fingers going on that. And then the future is going into accelerators, and in the next lesson I thought we could make something together a bit like we were on Blue Peter. Now if you haven't seen Blue Peter, you'll have to look it up on YouTube, but we're going to do a making together, and I'll lead you through the stage of you making something in the lesson for a bit of variety. Imagine the fun.